Ladies and gentlemen, boys and girls, welcome to another episode of Transparent Physics. In this lesson, we're going to wrap up our series on projectile motion with a superhero-themed Tier 3 problem. And our lesson goals really should be our lesson goal singular. We're going to work through a Tier 3 sample problem. Remember, according to Transparent Physics, a Tier 3 problem has a non-zero angle launch and a non-zero vertical displacement. In regular person words, that means it's launched at an angle that's not 0 degrees, and it ends at a different height than it started at. All right, for your pop culture minute for today, I'm going to explain to you what a fastball special is in the Marvel universe, if you don't know what it is yet. But first, I want to give my thanks to Matt Synowicz. Matt's illustration is featured in this lesson. He is an awesome artist. He designs toys, and nice guy in general. I emailed him out of the blue, asked him permission to use his picture, and he said, yeah, sure. So feel free after this lesson to take a look at his Tumblr feed. He has lots of amazing artwork, and I do really love his style. And thanks again for him letting me use this amazing picture in this lesson. Now, the fastball special, as shown in this illustration, features two superheroes, Colossus and Wolverine from the X-Men. Colossus is the shiny guy, and Wolverine's the smaller guy with the pointy claws, if you don't know. And in this move, Colossus, who's super strong, basically hurls Wolverine into battle so that Wolverine can get into the thick of it right away. So based on that classic comic trope, we're going to launch into a sample problem of our own based on this scenario. Alright, the scenario is as follows. Colossus throws Wolverine at a rampaging Sentinel robot. That robot is located 15 meters away. Wolverine's launch velocity is 19.5 meters per second at 60 degrees. And we're going to assume that Wolverine starts at ground level. That's just going to make things simpler for us. Colossus is standing in a ditch or something like that. And we're interested in Wolverine's vertical displacement when he impacts the Sentinel. So in terms of the important information, highlighting that, we've got our horizontal displacement, 15 meters. Wolverine's launch velocity is 19.5 meters per second at 60 degrees. Knowing that he starts at ground level just simplifies our problem a little bit. And then we're interested in the vertical displacement of Wolverine when he impacts the Sentinel. And again, that's back at 15 meters horizontal displacement. So let's see this one worked out. Okay, to save some time, we sketched out some of the details. To start, we've got Wolverine with a launch velocity of 19.5 meters per second at 60 degrees. And we are interested in trying to figure out at some distance further away, so that's 15 meters, we have a Sentinel robot, so big robot. Alright, Sentinel robot, and okay. And what we're interested in is we're interested in how high up Wolverine hits. So he is going to end up higher than he started. And we're going to call that dy. And that is our unknown. But we're also given the distance he is from the Sentinel. And that distance is 15 meters. All right, so if we plug stuff in, we know that dy is going to be our unknown. That's what we're going to be solving for. We do know everything we need to know about the initial y velocity and the initial x velocity, because we can break those up into their x and y components. So we do know that VIY is equal to VI times the sine of theta, and we know that the x component is equal to VI times the cosine of theta. And we have all that information handy, so we can just plug that information in. We can actually just get that right now. Why don't we just get that measurement either way? So 19.5 meters per second times the sine of 60 degrees, and 19.5 meters per second times the cosine of 60 degrees. So if you plug those into your calculator for VIY, I got 16.9 meters per second. And for VX, I got 9.8 meters per second. So that's good, that's handy. I'm going to follow my general rule here. We are not given any information about VFY. We are not asked for VFY. So I'm just going to, for safety's sake, I'm just going to take that off the table so we don't accidentally assign that as 0 when it's not supposed to be. Assuming they're fighting the Sentinels on Earth, G is negative 9.80 meters per second squared. And we know the dx value is 15 meters. So if we're looking for dy, what we're going to be interested in is, do we have enough information to start to figure out the value? And so looking in the y direction, we know that we have the initial velocity in the y direction. We have the acceleration in the y direction. But that's it. We only have two pieces of information. So we're gonna really be interested in solving for the time. If we know the time, then we have three pieces of information and we can solve for the vertical displacement. So there's not enough information in the vertical direction to solve for time, but there is enough information to solve for time in the horizontal direction. So if we take a look at our standard equation for projectile motion scenarios, in the x direction we have dx equals vxt, and remember again there's that plus 1/2 axt squared, but the acceleration in the x direction is 0, so that whole term just drops out. So we're left with dx equals vxt, and we know vx and we know dx, so we know two of the three pieces of information. So we're good here and we're good here, and so we can solve for the time. So we manipulated to solve for time. Time is equal to dx divided by vx, so that's going to be 15.0 meters divided by 9.8 meters per second squared, meters per second. Instinct is to say 9.8 meters per second squared, but it's just a coincidence. It's the same value here. When we do the math, you take 15 divided by 9.8 and you get 1.5, we'll say 1.53 seconds. Alright, so Wolverine is in the air for 1.53 seconds before he impacts the Sentinel. Now we can turn to the y direction and figure out our missing value. And so when we take a look in the y direction, we're going to use the Velma equation, but here nothing's going to zero out. So things are a little more complicated. We'll put a colon and an equal sign. dy equals VIYT plus 1/2 GT squared. Now on a lot of our earlier problems, something would have zeroed out here. Nothing does, so we just have to plug things in. Now we're not solving for the time, so that makes it easy. Easier. We don't have to solve for a quadratic, and we just plug our information in. So we have 16.9 meters per second times 1.53 seconds plus 1/2 negative 9.80 meters per second squared times 1.53 seconds squared. Do not forget to square the time. That is an extraordinarily common mistake in introductory physics. And you can go through, plug those values in, and you end up with a value of 14.4 meters. And that's positive, which we would expect to see because he's going up in the air. So in the duration of flying across to the Sentinel, Wolverine is 14.4 meters above the ground when he impacts the Sentinel after traveling a horizontal distance of 15 meters. So there you go, bub. All right, a few closing thoughts. Anytime you set up a projectile motion problem and you see that you're working with a tier 3 problem, again, a non-zero launch angle, and it ends at a different height than it started at, your physics danger sense should tingle a little bit, because these can be very challenging, specifically because nothing zeroes out in terms of the initial information. And when things zero out, that usually makes our math easier. In this case, however, I hope you agree that this wasn't like a super impossible problem. As far as tier 3 problems go, I would say it's on the easier end of the spectrum. But again, I caution that easier does not always mean easy. It still is a pretty challenging problem in and of itself. So hopefully you came out of that with a better understanding on how to do it. Okay, hey, if you think this lesson is going to help you out with your projectile motion problems, please consider liking the video. If you have any questions about how I solved it out, leave it in the comment thread below. And to help the channel grow and keep informed of what's coming next from Transparent Physics, click subscribe. As I'm thanking you for watching, I'd also like to thank two talented individuals. First, again, there's Kevin MacLeod, whose music from Incompetech.com is found in the background of all Transparent Physics videos, and also to Matt Synowicz for his awesome artwork. Check him out at his Tumblr account, and I will include the link to both individuals in the description of the video. This wraps up the projectile motion series, unless I can think of something else to add later. Hopefully you found that I've made things a little clearer for you with this series from Transparent Physics.